Welcome to this introduction to AutoTherm Desktop, a powerful engineering platform that's designed to maximize your productivity. AutoTherm is an interactive, automated workspace for mechanical engineers in the thermofluids discipline that provides a user-friendly environment with everything you need easily accessible at your fingertips. This platform can be viewed as a pyramid. At the lowest level, we have what we call the basic tools. These are the prerequisites with broader application than thermal sciences. These tools are located on the top menu towards the left. We have units and dimensions, constants and parameters, math tools and resources, and material properties tools and resources. Next, we have the main level fundamental thermofluids tools consisting of heat transfer, fluid mechanics, and thermodynamics. These tools are located on the top menu towards the right side. So we have heat transfer content here, fluid mechanics, thermodynamics, and we also have a section on numerical methods for heat transfer and fluid flow. And finally, at the top of the pyramid, we have the advanced tools developed for specific applications with distinct features. These tools are only available with special licensing. So what do we mean by tools and resources? Resources are organized contents that provide information about the subject in the menu item in the form of definitions, equations, tables, and graphs. These are like lecture notes taken from various references. As an example, let's look at convective heat transfer in channels or internal flows. So we go to the top menu, heat transfer, convective heat transfer, and we find internal forced convection. Now, as I mentioned before, these look like chapters in a heat transfer book. If you go to the end, you can see sections and you can jump to any section you want. We're going to start at the top. Once you click on the first item, as we can see, a text panel is opened up showing different sections for internal flow convective heat transfer. Starting with hydrodynamic considerations, definition of Reynolds number, mean velocity, velocity profile in circular pipes. Then it moves to pressure gradient, friction factors, and friction factor for laminar flow, and then Moody chart and friction factor for turbulent flow, different equations for that. Then we move to a section on thermal considerations, starting with the thermal entry length discussions, then definition of what we mean by mean temperature, fully developed considerations, energy balance, and then different surface conditions, uniform constants, surface heat flux, and constant temperature. And then we get to a section on Nusselt number correlations. First, in laminar flow, fully developed, the two famous constant values for Nusselt number for constant heat flux condition and constant temperature. Then we get into entry region discussions, which is important in laminar flow, and the Grates problem, correlations. And then we get into turbulent flow correlations, starting with the historical formulations, and then me moving into a much more accurate modern formulations, and the impact of rough walls, and then entry region for turbulent flows, and we finally move to flow in non-circular ducts. Now let's discuss the automated tools. These tools are standalone applications that utilize AutoTherm's basic tools for unit conversions, material property extraction, and various mathematical calculations. As an example, let's use the tool for the same chapter of internal flows. So again, we go to top menu, heat transfer. We go to convective heat transfer and internal force convection. You notice the tool is shown at the bottom of the sections. So if you click on that, a form will open up presenting an automated environment for studying internal force convection. Before we talk about the form, uh, notice that you can move this tool around or any of the tools. They're not attached to the main program. You can put it on a separate screen or you can open multiple tools at the same time. Now, if you look at this particular uh, automated tool, you can see at the very top, the first thing you need to specify is what is the fluid that's flowing in your channel. And you can do that by selecting a fluid from your fluids library, or alternatively, clicking on Enter Properties and enter your fluid properties yourself. Now, if you enter properties, of course, these properties will be fixed and these numbers will be used. If you choose a fluid from the library, the properties will be adjusted as the temperature changes and the film temperature changes. The next thing we need to provide is geometric information. If it's a circular pipe, you enter its diameter and length. If it's non-circular cross-section, you click on non-circular, and a form will open up allowing you to enter some values, pick your cross-section, and once you click OK, the value of hydraulic diameter will be entered here. The next thing we need to do is specify the flow information. You can do that by providing mass flow rate, volumetric flow rate, or velocity, average velocity at the inlet. Now, all of these can be entered and request output with any unit that you want. The last thing we need to give is thermal conditions. That means we need to provide an inlet temperature going into the channel, what type of surface condition we have. So as an example, let's say we have water flowing in a 1-inch diameter pipe that's 8 meters long with the average velocity of 1 meters per second. And inlet temperature, say it's 80 degrees, and we want to specify wall temperature at 25 degrees C. Once I click Update, it solves the problem and actually goes through a number of iterations until properties are stabilized. And for this particular case, we can see Reynolds number is a little over 50,000, which indicates turbulent flow as we expect, fully developed conditions. You have your average Nusselt number, heat transfer coefficient, and everything else. Now let's say we go ahead and change this problem, keeping everything the same except we change our fluid from water to engine oil. If now I press update, of course it will solve the problem again. But if you notice, the problem is completely different. Now we are Reynolds number 669, laminar flow at the thermal entry region. And if you look closely, you can see your Nusselt number average is 16.24, which is much higher than 3.66 value associated with the fully developed laminar flow with uniform surface temperature. That's because my default include thermal entry effects is on. If you didn't want it on or your flow was already fully developed, you click here and then press update, and you can see it goes to the known value of 3.66 for Nusselt number average. One last thing I would like to point out here is the panels on the right, which contain controls and supporting calculations. In the correlation corner, we see what correlation is being used for turbulent flow calculations. If you choose the rough wall option, you can see that the correlation will automatically switch to the recommended rough wall correlation, and you can specify a roughness value right here. At the bottom panel, we see the values calculated for friction factor, head loss, and pressure drop. And to the right of that, we see an area where you can specify what equation to use for turbulent friction factor calculations. Similar automated tools are available for all topics in heat transfer, fluid mechanics, and thermodynamics. As you can see, they are correctly positioned and easily identifiable. Let's say, as an example, we're looking for tools for transient conduction heat transfer. So if you go to heat transfer, we go to the chapter on heat conduction, transient, and we can see there are tools for lumped capacitance method right under its resources, spatial variation under its resources, and so on. Some tools utilize other tools to automate some calculations. One example of that is in the jet propulsion toolset. So if you go to thermodynamics, gas cycles, and the tool for turbojet engine, the automated toolset for that opens up. And the very first thing we need to provide is the local ambient condition, pressure, and temperature. Now, let's say we know the altitude and we don't know what the pressure and temperature is. So if we click on altitude tool, a fluid mechanics tool would open up and you can enter the altitude. Let's say we have 35,000 feet. And if you click update here, the results for pressure and temperature are automatically entered into the text boxes. Hopefully this gives you an idea of what tools and resources are and how they work. We will have many detailed videos with solved problems for all of the tools. Thanks for watching this video.